just like in even reactions, even in E2 also, you need a good leaving group. A good leaving group is required. I told you what a good leaving group is. Okay. Let me also give you an example. See, this is called trifluorosulfonic acid. And when it loses a proton, we get CF3SO3 minus. So this is of course called triflate ion. It is in fact considered to be a super leaving group. It is because trifluorosulfonic acid CF3SO3H is the strongest acid. Its conjugate base is the weakest. So is the super leaving group. Okay. SO3H is the strongest acid. Its conjugate base is a CF3SO3 minus. And this conjugate base is weakest. Okay. So it is a super leaving group. Then coming to the reactivity order. This is very interesting. The reactivity order for E2 is 3 degree, 2 degree, then 1 degree. In case of different types of alkyl halides, this is the order: 3 degree, 2 degree, and 1 degree. It is because in case of a 3 degree one, a more stable alkene is formed. Whereas in case of 1 degree, a less stable alkene is formed. Okay. I'll give you examples. But interestingly, even in case of E1 also the order is same, but reason is different. It is the same order, even for E1 also. But we know that the reason is not the same. The reason here is the stability of the carbocation. I told you that in E1, because in the rate determining step we get a carbocation, stability of the carbocation plays an important role. So reason is same, reason is different, but the order is same in case of E1 and E2. Okay. Now, seen almost all the E2 reactions, said the product is the major one. But there are 4 exceptional cases, very important. Except in 4 cases in which we get Halfman product as the major product. I'll give you all these. But first, let us take some 1 or 2 regular examples for the subject thing. Concentrate on these examples. See, this is what is given. It's a 3-degree alkyl halide, right? Now, of course, this carbon is alpha. This one is beta. Even this also is beta. Even this also is beta. But these two are in the same environment. Either you go that way or this way. Doesn't make any difference. Right? Now, let us see what all are the possibilities that we have. See, these 3 are in the same environment. So any of these is okay. Now, at this. Hydrogen and hydrogen. Even these 2 are in the same environment. These 2. Now, these are the possibilities. Let us use a strong base. Told you to go for anion. Now, no doubt, this is going to go out. But what is that beta hydrogen that comes to the rescue of this carbon, which is going to get partial positive charge in the transition state? Yes, of course, there are 2 possibilities. Either this, any of these 3. Let me take this one. This, let us consider it as possibility A. Or else any of these 2 may come here. This is possibility B. Check this out properly. Now let us see the product in the first or the possibility A. What do we get? Come on. Simple. This is where you get a double bond. In this particular case, we got A. Then go for B. Now, this is what you are going to do. Okay. Now, the bond will be here and you'll be left with your CH3 as it is. Now, let us compare these two products. I think you are very clear about these two. See, here the double bond is outside the ring. So let me call this exocyclic double bond. Whereas in this one, we got the double bond inside the ring. So is endocyclic. In general, the endo is more stable when compared to exo. Of course, the reason is again the same basic one. Check out the hyperconjugation or check out the substitution. You know, here, just like what we discussed yesterday, the two hydrogens are still there, not being substituted. Of course, here, for this carbon, you got two substitutions, substituents. Both the hydrogens have been substituted. So, check this out. Here, there is only one hydrogen left unsubstituted, and that is this hydrogen. In the first one, there are two hydrogens left unsubstituted, whereas in the second one, there is only one hydrogen left unsubstituted. So we can say that this is a lesser substituted, therefore lesser stable. Lesser substituted, of course, is said to be Hoffman product. Discussed. Now this one, this is more substituted, more stable, and of course, said. Clear. Less substituted because we still have two hydrogens left. Less substituted is always less stable because it will have less number of hyperconjugative structures. Okay, then more substituted is more stable. Of course, the more stable one is called ZF product. It is more stable, it is more substituted. More stable because of more number of hyperconjugative structures. Okay. So this is a regular ZF product formation. Now, let us take the exceptional cases. Very important. See, there are 4 exceptional cases. The first one is when the leaving group is poor. Okay. You know what a poor leaving group is? Fluoride. In fact, fluorine among the halogens is a poor leaving group. Told you earlier. Now, if you want to remove fluorine, which is already a poor leaving group, see, you got two possibilities here. This is, of course, alpha, beta. This also is beta. You can remove either this hydrogen or this hydrogen. See, removing this hydrogen is easy because fluorine is a poor leaving group, but here there is something which is bulky and there will be some steric hindrance. So rather than this, you can easily remove this. And when that is removed, okay, let us consider both the possibilities. Let this be the possibility A and let this be B. With alcoholic KOH, in possibility A, of course, that is very easy to remove. This one. Now this is, as you can see, a lesser substituted one. Even here also there is one hydrogen left unsubstituted. So this is a lesser substituted one. But still, as I said, in this case, removing this hydrogen is easy. So here the Hoffman product is major. Because the fluorine is reluctant to leave. If you want to make it leave the substrate easily, of course, you can eliminate that along with this hydrogen, which is easy to remove. Then this B, because of this steric hindrance, the bulky group, the larger methyl group that is present, removal of this beta hydrogen is little difficult when compared to this, the first one. Now we get this. This is your Sedgwick product. Sedgwick product, but this is minor because the removal of this beta hydrogen is difficult, whereas the removal of this is easy. So in this case, steric hindrance, actually in all the four exceptional cases, steric hindrance plays an important role. Now check the second one. The second exceptional case is when the leaving group is bulky. Right? When the leaving group is bulky, like for example, NR3 plus, SR2 plus. Now, when these groups are present, let us take an example. Yes. Consider this. Now you got a bulky group as the leaving group. Even here also, of course, you got two options. This again is bulky. So removal of this beta hydrogen is easy compared to this beta hydrogen. Let this be the possibility A and this be the possibility B. Right now, this is what you get very easily. This is a lesser substituted one. Of course, Hoffman product. In this case, it is major because the bulky group can go along with this hydrogen readily. Whereas with this hydrogen, it cannot go that readily. Now, yes. So when this hydrogen, I mean B, is removed, we get ZF product. ZF product is minor in this case. Okay. So the first one is when the leaving group is poor. Now the second one is when the leaving group is bulky. The third exceptional case is when the base is bulky. The base used is bulky. Let me give you an example. Sodium tertiary butoxide, a bulky base, a sterically hindered base. Okay. Now this base can abstract this hydrogen readily. I mean, this beta hydrogen can be abstracted readily rather than this beta hydrogen. This is possibility one. This is the second possibility. See, the base can easily abstract a less hindered one rather than the more hindered one. Now, possibility A gives us this product. Which is Hoffman type. But this is major here because the bulky base or the sterically crowded base can easily abstract this hydrogen rather than the second one. Now B. So this is ZF product. This is minor. Okay. So the third one is when the base is bulky, we get Hoffman product as the major one. Reason is again the same. Now the last one is when the gamma carbon is quaternary. Yes. Let me give you an example. This one. What is gamma carbon? This is alpha, this is beta, this is gamma. Gamma carbon is quaternary. Yeah, you can see that this is a very big group. Too much bulk here. So, of course, this is again a beta one, but easy to remove as you can see when compared to this. This is difficult to remove. Simple. With alcoholic KOH, a stronger base, possibility A gives us this product. Yes, this is Hoffman product. Of course, major. Whereas when you go for the second possibility, this is what you get. Right? This is ZF product. But this is minor. Now, these are the four cases in which we get Hoffman product as the major product. You have seen why. More specifically, it is the steric hindrance at one of the beta carbons that makes it to undergo a kind of elimination to give a Hoffman product as the major one. Okay. First one is when the leaving group is poor. The second one is when the leaving group is bulky. Third one is when the base used is bulky. And this is when the gamma carbon is quaternary. So these are the four exceptional cases wherein we get Hoffman product as the major one. Very important.